We'll discuss sequence and series of functions. So we say a sequence of functions f(n) of x defined on, say, set E converge to f if for a given x we have the following: for every epsilon positive we have every n greater than n epsilon and x. So this n integer is a function of both epsilon and a value at which we are checking the convergence of the sequence of functions. Now, this is the definition of convergence of sequence of functions. So, if say fn's are continuous, then we're going to get an pointwise convergence. So this is pointwise convergence. And so if fn's are continuous, the limit need not be continuous. So one standard example for this is square by 1 plus x square whole power n. Now let's define Sn of x be sigma k is equal to 0 to n x square by 1 plus x square raised power n raised power k. So these are continuous functions. So the sum finite sum is also continuous. But then as in the limit as n tends to infinity, Sn of x, let's call this as f of x, so when x is not equal to 0, this thing converges to 1 plus x square, x not equal to 0. At x equal to 0, this value is 0. You can see this for every finite n, this is continuous, but the limit, this becomes discontinuous at x equal to 0. So So another example of this is fn of x sine nx the square root of n. So in the limit, this fn of x goes to 0. Define it as f of x. But fn prime of x is square root of n cos of nx. Now if we take a limit, this implies f dash of x is 0 here. N tends to infinity. Fn dash of x is not equal to f dash of x. So to have this notion of interchanging limits and by doing the operations such as differentiation, and in the other example we saw that summing. The issue is the pointwise convergence. So this brings the notion of uniform convergence. Um, yeah, a sequence of functions fn converge to f uniformly. Then we have this fn of x, f of x, fix an epsilon. Then for all x, there exists an epsilon such that n greater than n epsilon. We have this holds. All right. So can talk about one more example that in general limit n tends to infinity integration over some set, say E fn is not equal to integration of f over A, where limit n fn equals to f pointwise. One standard example here is say fn of x so we have limit n tends to infinity. Fn of x is 0 because this is n square is polynomial and this is exponential in n, so it dominates n square. And hence this goes to 0 much faster than this, right? So now integrating a 0 function is 0, right? So here we have this thing, integrating limit n tends to infinity, fn of x is 0. Now we integrate fn's and then let n tends to infinity. So if you integrate n this thing, x into 1 minus x square whole power n. Into n square. This is equal to n square by 2n plus 2. Now, if you let n tends to infinity, this approaches to infinity. So this is not equal to limit n tends to infinity of n of x dx. So this is because it converges pointwise to f. So once we have uniform convergence, we have all these properties. We can interchange, we can pass the limit through integrals. So let's solve some problems. So define key norm. N is equal to 1 to n. The k is equal to 1 to n. Mod x k p whole power 1 over p. Now, is this a norm? So to check a norm, we need to have this thing, definiteness. If x equal to 0 and mod alpha times norm x. So we can check this. So this is obvious if this is 0 because each of we are summing each of them positive terms and then taking the p through term. So this is 0 if each of the entries and inside the sum is 0. So this implies the first property is fine. And to check the second property, let's do this. Alpha x p is sigma k is equal to 1 to n. this is equal to once we satisfy the second property as well. Now the third property is the triangle inequality. This follows from Minkowski's inequality. For n greater than or equal to 1, this holds. So it's norm when p greater than or equal to 1. So here the question is, if norm xn goes to 0, then is it true that this is true? Because for say p is equal to 2, we always have this inequality 2 norm is less than or equal to square root of n times the infinity norm. And this is greater than or equal to the infinity norm. So this can be written as d x belongs to r by t, let's say. So here we can see that a norm, 2 norm is sandwiched between the two scales of infinity norm. So infinity norm goes to 0, then it has to go to 0. So that's why this is true. we are given a function fn of x. Suppose fn of x converges to 0 pointwise. Um, then is it true that fn converges uniformly to 0? So this is wrong because say any function fn of x converging to some function f pointwise, then define Sn of x to be fn of x minus f. So this Sn converges pointwise to 0. But then this doesn't imply that Sn converges uniformly to f uniformly to 0, but then otherwise fn of x would have converged uniformly to f. That would imply pointwise convergence is same as uniform convergence, which is not. So the question is, f is differentiable. F dash of exists implies f dash of exists everywhere. And f dash of x is bounded and f is not uniformly continuous. So here is this thing. We have this say f dash of x is bounded by say some value L. Let's write down the Taylor series of f around a point x. So this term goes to 0. That implies we'll have this. So notice that if, let's put this, if y minus x is less than epsilon by m, then f of y minus f of x is less than delta. This is an epsilon. So this condition is nothing but uniform continuity. So whenever we have this, if dash of x is bounded everywhere, this automatically implies Lipschitzness. So this is L. This is L. And once this is Lipschitz, then we have uniform continuity. Finally, we have this Fn. Fn's are Riemann integrable functions, and then f maps AB to R is Riemann integrable such that Fn converges to F uniform unit to B. Then we have this. So whenever we have Fn converges to F uniformly, then so we can pass the limit inside.